Hello everybody, it's Mrs. Pound and I am back with the last video for chapter 27 on light. This is a short chapter, but there are a number of chapters on light, so these are all going to be short, fast chapters. So our objectives for this video are to describe the conditions for solar and lunar eclipses, cite evidence that light waves are transverse, and explain why Polaroid sunglasses are helpful in cutting sun glare from horizontal surfaces such as water and roads. So shadows first. To understand shadows, we have to understand that a ray is a thin beam of light. We're going to be talking about light rays a lot in the coming chapters. And a shadow is a shaded region in the far side of an object where light rays cannot reach. And we can see all the shadows from these trees. Now, when we talk about eclipses, there is something called the umbra. This is the darker side of a shadow where all the light is blocked. And behind this, in the picture in the background, you can see a solar eclipse. And a penumbra is a partial shadow that appears where light from part of the source is blocked and light from another part of the source is not blocked. And in the background, you can see a lunar eclipse happening. So here are some pictures of a solar eclipse and a lunar eclipse. And here for the solar eclipse, we can see that the moon must be between the sun and the earth for the moon to cast a shadow on the earth here. And the moon has to always be in the new moon phase for a solar eclipse and to happen. And as you can see, you're only going to get that total solar eclipse on part of the earth where this shadow is happening. And this is the umbra. Out here is the penumbra, where you have that partial shadow. And so areas there will see a partial solar eclipse. The whole sun will not be blocked out, just part of it. Only here in the umbra will you see a total solar eclipse. For the lunar eclipse on the bottom, you can see that this Earth is between the sun and the moon, and the Earth is actually casting its shadow on the moon. The moon must always be in a full phase of the moon. So you must have a full moon. And here, this is the umbra. You're going to see a total lunar eclipse here. This is the penumbra out here where you would see a partial lunar eclipse. Now, solar eclipses are seen less commonly than lunar eclipses because the Earth's shadow on the moon is larger than the moon's shadow on the Earth. And we can see that again here, just so much more common because of the way these shadows are. Now, not really related, but I lumped this together just because I didn't want too short of a video. So our next topic is polarization. Polarization is the aligning of vibrations in a transverse wave, usually by filtering out waves of other directions. When these waves get sent out, the transverse waves are going this way, they're going this way, they're going this way, they're going all kinds of ways. Okay? Polarization is making them so that they're all going, say, this way. Okay? That's what polarization is. Polarized waves are not separated into opposite phase because crests and troughs are not canceling. This is not cancellation. This is actually filtering of them out using special lenses. And I will show you this in class. I have some polarization film, some Polaroid film that we will be experimenting with this. Now, if two polarized filters are held with their polarization axes at right angles to each other, the amount of light transmitted compared to when the axes are parallel is 0. Okay? When you have, they have like, it's almost like oven grates that when the polarization filters are going this way and this way, those waves are just all canceled out. Now, grazing light reflected from a lake is polarized horizontally, and even this, I can almost see the glare coming off of this. It's all coming off horizontally. So what you can do is you can take and you can wear Polaroid glasses that cut down on glare. They will polarize the light vertically, and so you get less sunlight in through those glasses. You don't get that glare off of a lake or a road. So these kinds of glasses are commonly used as sunglasses, especially for sportsmen or for driving. Now, Polaroid light is also used for 3D movies. So Polaroid light is used to create the illusion of depth in 3D movies. The first thing that they do is they take a pair of movie frames and they film them a short distance apart. So you wouldn't just have one movie camera, you would have two movie cameras filming the scene. The second step is there's the pair of movie frames are projected through polarization filters at right angles to each other. So then you have two projectors. They each have a polarization filter like I'm going to use in class. One would be vertically, one would be horizontally, and the film is passed through those. The third step is the viewer wears polarizing glasses with lens axes at right angles. So not only is the film going through polarization filters, you're wearing polarization filters. So your eyes will only see one frame on each side, not both. Otherwise, it does appear blurry because the projection on the screen is actually offset a little bit, so it looks blurry. But if you're wearing the glasses, only the left polarized or the vertically polarized can go through one eye, and the horizontally polarized can go through the other eye. So each eye sees a separate picture, just like in real life, and the brain interprets the two pictures as one picture with depth. So it's playing tricks on your brain, and we're going to take a look at some other pictures in our book where our brain interprets things and we see things that aren't really there as well. So our objectives were to describe the conditions for solar and lunar eclipses, cite evidence that light waves are transverse, and that evidence is because of the way they go through the polarization films, and explain why polarized sunglasses are helpful in cutting sun glare from horizontal surfaces such as water and roads. So don't forget your 5 questions, and you have all the information you need to study for the Chapter 27 test. So I'll be back with more about light in another chapter.